Welcome to This Explainer. Today, we're completely demystifying the math powering AI. If you've ever felt overwhelmed by the technical jargon surrounding artificial intelligence, you are absolutely in the right place. We're going to prove that AI doesn't rely on some secret, magical branch of mathematics discovered beneath a volcano somewhere. Instead, it relies on familiar, everyday operations that are simply executed at an extraordinary, mind-bending scale.
To alleviate any math anxiety right out of the gate, here's our roadmap for today. 1. Demystifying AI math. 2. Vectors and embeddings. 3. Measuring vector similarity. And 4. How vector search works. No surprise pop quizzes, I promise. Just clear concepts step by step. All right, let's jump straight into section 1. Demystifying AI math and the reality of what's actually going on. Let's tackle the biggest barrier directly, which is really our own perception. We usually imagine AI math as this terrifying nightmare of complex symbols, surprise calculus ambushes, and honestly borderline wizardry just to run a program. But the reality? It's literally just lists of numbers. You're adding, multiplying, comparing, and then repeating that process a whole lot. It's basically just basic arithmetic turned into a superpower through massive, massive repetition. To break this down a bit further, most AI systems run on what we can playfully call the four math food groups. These four foundational pillars work together to take inputs from the real world, text, pixels, audio, and turn them into numeric representations that a computer can actually chew on. Let's quickly look at what each one does. First up is linear algebra. Now, think of linear algebra as the math of handling big groups of numbers as a single unified unit. It gives us a highly efficient way for computers to represent and transform massive sets of numbers all at the exact same time. Next, we have probability and statistics. This is your mathematical foundation for finding patterns and dealing with the unknown. In AI, this is exactly what allows a system to reason properly about uncertainty, weigh different pieces of evidence, and make really educated predictions based on patterns it's seen in the past. The third group is calculus and optimization. Picture calculus as the engine of improvement for an AI. It is constantly working behind the scenes, tweaking parameters and adjusting the model so that the system makes fewer and fewer mistakes over time. It's all about reducing the error rate on whatever the AI is trying to achieve. And finally, rounding things out, we have algebra and functions. Algebra provides the core rules that actually let a model operate, because at the end of the day, a model is really just a giant function. It takes an input, uses defined mathematical relationships, and reliably turns it into an output. Moving right along to section 2, vectors and embeddings, or how we actually turn human meaning into coordinates. Okay, so it all starts with a vector, and a vector is really nothing more than an ordered list of numbers with a specific job. It describes a position, a direction, or a set of characteristics. It's just a remarkably clean way of packing complex information into a simple mathematical list. To make this concrete, imagine a 5-number vector that represents you. We can take abstract human traits and map them directly to numbers. So let's score these traits on a scale, say 0 to 10, or using actual years. You get a 6 for introversion, an 8 for your love of coffee, 12 for years in tech, a 4 for risk tolerance, and a 2 for being a money person. Suddenly, your complex human profile is just the list: 6, 8, 12, 4, 2. Now, when we compare your vector to a colleague's vector, a story instantly pops out of the data. You've got that strong coffee alignment and a frankly concerning morning score of 2. But your colleague, they've got a totally different risk profile at a 7. And with a morning score of 9, they are suspiciously functional at 7 a.m. Even without calculating any formal distance, we can just intuitively look at the numbers and see exactly where you are similar and where you drastically differ. And this brings us to embeddings. When an AI model learns to take real-world concepts, whether that's a person, a word, a whole paragraph, or an image, and map their characteristics into a shared numeric space, that result is called an embedding. The real magic here is this: things that are close together in meaning end up close together in math. Which leads us perfectly into section 3, measuring vector similarity, basically finding the distance between meanings. You've probably seen this famous equation before: king minus man plus woman approximately equals queen. Now, it looks like pure enchantment, right? But it is actually just learned geometry. The AI is simply calculating the exact distance and direction that separates the concept of man from woman, and it applies that exact same trajectory to king to land right near the coordinates for queen. So, to measure how close these concepts are in that space, AI relies on something called cosine similarity. Don't let the term intimidate you. It basically just asks, hey, are these two vectors pointing in the same direction? It uses a calculation called the dot product to measure that alignment. And then cosine similarity normalizes it based on the length of the vectors. So we literally only care about the angle between them.
The visual intuition here is remarkably simple. If the directions align, meaning the angle between the vectors is small, boom, you have high similarity. The concepts are highly related. But if the directions completely diverge and the angle is large, you have low similarity, meaning the concepts are unrelated. The score is just reflecting the angle between those lines. Let's move to our final section, Section 4, how vector search works and how we compare our queries with stored math.
The crucial point to grasp here is that vector search, which is the absolute engine behind modern AI retrieval, is just 3 straightforward steps. First, you embed the query. That means you convert the user's search request into a vector using the exact same approach used for the data. Second, you compare the score. You're looking at the directional alignment between that query vector and your stored document vectors. And third, you return the neighbors. You literally just retrieve the mathematically closest items to answer the prompt.
You are often going to read incredibly dense technical sentences about this, like the retriever computes the cosine similarity between the query embedding and each document embedding. But let's do a plain English translation here. The search system just ranks documents by how similar they are to the question. That's it. The mathematically closest candidates are the ones that actually advance to your screen.
As we wrap up this explainer, I want to leave you with a final critical boundary check to apply to literally every AI system you encounter. We've learned that AI search relies on plotting concepts as coordinates and finding whatever's close by. But remember, proximity is just a math calculation. So if a document is geometrically the nearest, mathematically, does that actually mean it is factually correct? It's a vital question to keep top of mind as you navigate this AI-driven world. Thanks so much for joining me to decode the math behind the machine.